Hello, everybody, and welcome to today's Via Satellite Technology webcast series episode titled Orbit Ready Testing Engineering Success in New Space Innovation, presented by Square Peg Communications. My name is Jeffrey Hill, Executive Editor of Via Satellite and Executive Chairman of the Satellite Show in Washington, D.C. Thank you all so much for joining us today. During the next half hour, we'll be joined by Square Peg Communications RLS Product Manager Colin Telfer, who will deliver a presentation on how testing plays a pivotal role in driving innovation and ensuring success in an era of new LEO satellites, multi-constellation networks, and advancements in 5G, IoT, and NR. He will also share experiences from his company's collaboration with the European Space Agency on their Space for 5G project, as well as providing a 101 guide to testing fundamentals for new space, how the right testing approach supports the rapid pace of new space development. But Colin is currently responsible for Square Peg's radio link simulator product line. He has more than 20 years of experience in data and voice communications, including real-time embedded software development and RF testing and evaluation. And we're very lucky to have him with us today. Colin, good to see you. Before you start, just want to let our attendees know, if you have questions for Colin, please submit them using the Q&A tab on the right-hand side of your interface here, and we'll get to those if we have time at the end. But without further ado, I'll turn this over to Colin and for his presentation. Colin, thank you so much for being here, and good luck with your presentation.
Great. Thanks, Jeff. It's great being here. And on behalf of Square Peg Communications, I'd like to thank all of you for joining today. So, my name's Colin Telfer. I'll be presenting today. I'm product manager of the RLS 2100 Radio Link Simulator platform. And Square Peg Communications has been in the satellite communications business for over 25 years, providing solutions for ground stations through to user terminals and everything in between, with a strong focus on satellite link testing and test equipment. So today I'm hoping to pass along some of our testing knowledge, and specifically for orbit ready testing in new space applications. So here's what we're going to cover today. First, we'll set the stage by talking about the current state of satellite communications. Then we can share some of our key findings from an amazing project with the European Space Agency for 5G non-terrestrial networks. Next, we'll dive into testing fundamentals for new space. In here, we'll give you insights on how to efficiently test your new space applications, covering methodologies and test equipment to meet your testing goals. This will be followed by a few real-time demos where we'll see some real testing in action, and then wrapping up with a look to the future. So today we're experiencing an exciting period of rapid innovation in satellite communications. With launch costs plummeting thanks to the likes of SpaceX, the barrier to entry to space is falling. This is opening the way for a number of new players into satellite communications with some big ideas and ambitious plans. It seems we are poised on this inflection point, straddling today's innovations and tomorrow's new space frontiers. On this slide here, just showing a few examples of the space technologies that are taking shape today. So we have mega LEO constellations, satellites now in the hundreds and thousands, standardization in satcom with 5G non-terrestrial networks, for example, massive IoT applications applied to everything from disaster mitigation to vehicle diagnostics and efficient farming, complete global connectivity, so with the promise of low latency and high throughput spanning the globe. And beyond the globe, we are now talking about lunar comms infrastructure. So just last week, we witnessed a private company landing on the moon. So an incredible achievement. And we can really start to imagine the many applications for lunar-based satellite communications. So we can speak about new space in terms of these amazing technological advancements, but also in terms of a new mindset. Space is no longer reserved for large enterprise and government programs. And large geosatellites are being replaced with dynamic and flexible constellations of LEO, MEO, and hybrid networks. Development cycles are getting shorter, and the scope of satellite missions are getting wider. Competition is really heating up in space, and new companies and incumbent operators are innovating to stay ahead. So it's really an exciting time, but these advancements are coming with increased complexity. This next section actually provides a great example of new space mindset and technology. The European Space Agency's 5G, Space for 5G strategic program line is an ambitious project to facilitate adoption of non-terrestrial networks to enhance global 5G connectivity beyond what's possible or even practical with terrestrial alone. In this program, the European Space Agency, or ESA, has embraced the value of testing to further these goals. They're building test platforms that allow stakeholders to demonstrate new technology, investigate proof of concepts, verify system integration, and optimize performance. And SquarePeg was chosen to help with this test infrastructure, in particular, in this case, for hybrid terrestrial satellite connectivity. The challenge here was to develop a simple, cost-effective, integrated platform to rigorously test hybrid networks. It is critical to recreate 5G scenarios with handovers between satellite links and terrestrial links in the lab with actual equipment at RF. ESA needed an easy-to-use solution to solve a complex testing challenge. So here, SquarePeg leveraged our deep knowledge of physical layer testing and applied our wideband radio link simulator platform to meet this challenge. So we can see here that trying to test 5G hybrid networks with existing test equipment would be daunting. If we consider just a list of devices that would be required, you can start to get a sense of that complexity. So thinking of this, we would need a satellite channel emulator, a terrestrial channel emulator, orbital modeling software, signal generator, GPS simulator, RF switches, frequency translators, spectrum analyzers, and a test controller to try and tie all this together. And now trying to synchronize all this equipment would be difficult and costly. So SquarePeg replaced all of this equipment with a single integrated platform, the RLS 2100. This allowed users to set up realistic and complex scenarios easily, and with tight synchronization amongst all the elements in this platform. So there are a number of key learnings from this integrated approach for 5G non-terrestrial network testing. As shown on the previous slide, having too many boxes to control drives up the complexity of test setups and the interfaces to control them. Whereas having an integrated device reduces the equipment cost of a test setup, it reduces the synchronization challenges, and it makes configuring tests much easier. Having hardware in the loop was critical for orbit-ready testing. Hardware in the loop allows real equipment to be connected in the lab at RF, and we found that satcom equipment doesn't always perform as advertised, in particular when multiple elements are under test and are integrated together with varying channel conditions. For ESA, allowing device manufacturers to plug real equipment into a network test bed demonstrated how close these 5G NTN applications were to deployment. Another key was having accurate scenario modeling. Working with approximations can be useful in some testing if we're varying maybe one or two variables. But if we want to recreate real-world scenarios in the lab, the number of changing variables can be numerous. And so having accurate channel models supporting dynamic changes in real time was critical. Although there was many similarities between satellite and terrestrial over-the-air links, in some areas the difference between them was significant. So delay being the obvious one, microseconds for terrestrial links versus tens of milliseconds for satellite, but also the channel models for reflected paths, shadowing, and blockage, amongst others. And these critical nuances between channels couldn't be overlooked when testing hybrid channel operation. was important to have timing accuracy and synchronization in the testbed. The requirements on tight timing in 5G are crucial for proper network operation. A slight error in round-trip time can mean the difference between a successful connection or a failed test. Covering the full FR1 and FR2 frequency range wasn't trivial. The test platform required precise RF calibration for amplitude and phase across the 30 gigahertz span of 5G frequencies, ensuring that no unwanted RF effects were introduced in the testing. We recognize the need for repeatable and automated testing. With the scope and complexity of 5G networks, you can imagine the number of tests to be carried out. So automation was essential for continuous testing. And lastly, to accommodate the many different users for the 5G hybrid test setup that ESA was planning, it was important to have a flexible platform, one that was easy to reconfigure on the fly and quick for setting up different scenarios to cover the many use cases presented by users. So really, this project of the European Space Agency to develop an integrated hybrid test platform for 5G highlighted just some of the challenges of new space applications. As the complexity of satellite communications continues to scale up, this presents a never-ending series of challenges for the test engineer. Let's dive into just one example of new space complexity. It's a hot technology right now, so direct to cell. If you consider current terrestrial cell networks, although most of us take it for granted, there's significant complexity in managing your phone's connection with a nearby tower. Now imagine putting that cell tower in space, 500 kilometers straight up. We go from microsecond delay to tens of microseconds of delay. Now imagine your cell tower whipping overhead at a speed of approximately 8,000 meters per second. So now this introduces rapidly changing path loss, path delay, and large Doppler frequency shifts. And of course, traveling at that speed, the tower won't be overhead for long. So now we need a series of towers or satellites. We need to hand over between them every 5 to 10 minutes. So under these conditions, how are we going to guarantee that a user has a seamless connection? Clearly, testing is going to play a key role here. For satellite communications, we're constantly working against the channel characteristics of free space to pass our data uninterrupted and efficiently between transmitter and receiver. In addition to the path loss, delay, and Doppler, there's many other challenging channel conditions like atmospheric conditions, rain fade, noise in all forms, shadowing effects, blockages, reflected signal pass into the receiver, antenna effects, interferes, and more. So to deliver robust satcom services, we need to test for complex conditions. Let's review the fundamentals of satellite link testing. We need to start by anchoring ourselves on solid grounding with key testing principles. In addition to new technology and these unpredictable channel conditions, we have to navigate agile development practices for new space projects. Agile methodologies promote continuous innovation throughout development cycles. Complementary testing practices are critical to the success of these methods. We have to test early. This is how we identify showstoppers and design flaws. This allows us to pivot in strategy and improve design. Testing provides the greatest return on investment when it is implemented at the earliest of stages. We have to test often. Testing regularly allows for continuous integration and innovation to match agile development. We can adapt to changes through testing feedback and add value to keep up with competition. We can't wait for a near finished product to run our tests. We have to test rigorously. We need to strive towards testing all corner cases and under all conditions, with strong traceability to every requirement. This will eliminate the surprises that are very costly to fix in the field, or even impossible to fix when in the field means space. And we must test with precision. So having an accurate representation of real-world scenarios is where the true value of tests can be realized. Our devices have to perform at the highest level. They cannot be the source of errors in our testing. So precise test beds provide confidence in test results. Now, it's easy to preach these fundamentals, but not always so easy to implement them. Testing has to be easy or we won't do it. Testing can't be cost prohibitive or someone finds a way to drop it from the budget. And testing can't take too long or we find ways to cut corners. So what can we do to help with these implementation challenges? So one way to help us in following these testing fundamentals is having the right tools for the job. The RLS 2100 is an example of a test tool that was developed as a direct response to new space testing. It was built to put these fundamentals of testing into action. If we think about the things that help us testing early, one way is to use hardware-in-the-loop testing. With hardware-in-the-loop, we don't have to wait for a satellite to be in orbit to start testing our data links. The RLS 2100, a hardware-in-the-loop emulator, allows users to bring their satellite links into the lab with physical hardware simulations using real equipment, terminals, and modems, and proof of concepts and risk reduction activities can take place at the earliest stages of development. If we're going to test often, it has to be easy. Test setups need to be simple to configure, and we need automated control of our test devices. The RLS 2100's graphical user interface makes it quick and simple to set up repeatable tests. It has a powerful functional API for test scripting and automation. To test rigorously is no longer enough to have a single-purpose test setup. New space applications are introducing more flexibility into the mission, like multi-orbit and elastic payloads. The RLS 2100 is highly configurable and can be reconfigured in real time. This is made possible with integrated channel modeling for any satellite orbit and any land mobility scenario. And for testing with precision, test equipment must be able to apply channel characteristics accurately and precisely. SquarePeg takes pride in delivering high-performing test equipment for satellite communications, and the RLS 2100 here is no exception. So as we've learned here, testing in new space can be challenging, so having the right tools for the job saves time, money, and frustration. Okay, so now we get to the fun part. I'll put aside these slides now, and I have a series of real-time demos. So 3 real-time demos. These illustrate real-world application of our testing principles using the RLS 2100. So we'll start with a simple scenario here and then gradually increase the complexity. With these demos, we hope to show how satellite communication challenges like Doppler shifts, changing path delay and path loss, handovers, and more can be navigated in new space application. So let's jump in to do some real testing here. In order for me to show this video, bear with me. I might need to take a second. Okay. Actually, start with the slide here. So so for our first demo, we're going to use the RLS 2100 to simulate a stationary user terminal on a plane that happens to be parked at JFK in New York at the airport, and with a single LEO satellite passing overhead. So here we'll focus on the basics of Doppler shift, changing path delay and path loss in real time as the satellite moves across the sky. For this demo, we have a satellite modem set up in the lab. It's transmitting a signal through the RLS 2100. And the RLS 2100 is applying these varying channel characteristics to the link to match this scenario that's unfolding. So now I'm going to share this video of the demo. Right. So here we have the demo in action. And here we have a user terminal in New York on the tarmac. And we have a LEO satellite approaching up over South America. Currently, the RLS 2100 is simulating this link between the user terminal and the LEO satellite, or lack of a link. But as the elevation angle changes and the LEO satellite comes into line of sight, and on the right-hand side here, we have our internal spectrum analyzer in the RLS 2100. And this is showing the satellite signal from the modem coming through the RLS 2100. So you can see the signal is passing through with some Doppler shift. It's off center. We have a positive Doppler frequency shift as this LEO satellite is approaching the user terminal. And we have this delay profile that's being plotted here. And so we see as the LEO satellite is approaching the user terminal, the delay is decreasing. Now this is sped up. This is a 15-minute window compressed into about 3 minutes for this video. And so things are happening a bit quicker than in real life, but it really gives the ability to see what's happening in a full overpass of a LEO satellite over the user terminal. So we can see these changing channel characteristics and delay profile as the terminal to LEO satellite link is experiencing these channel characteristics. This could be a really nice test setup for a terminal or a modem developer to have on their bench and recreate this LEO scenario. I'm going to stop sharing that one. Back to the slides. So we're going to move to demo 2 here. And so in demo 2, we're going to ramp up the complexity a bit here as we're going to simulate a constellation of satellites. So with the same terminal on the ground at JFK, we're now going to introduce beam handovers as the link from the user terminal to the LEO constellation now is jumping between satellites. So we have the same hardware set up, but now the satellite modem will believe it has a link through a constellation of satellites instead of just a single LEO. So let me go back to sharing a video here. Okay, so what I'm sharing here now is a demonstration of a LEO constellation. So we have the same user terminal sitting at JFK Airport, but now we have the RLS 2100 modeling a full constellation of satellites. I think it's around 200 satellites here. Each satellite is depicted by a red dot on this scenario window. And so the RLS 2100 in real time can be modeling the motion and position of all of these satellites, but it is applying the link characteristics of the active satellite from the user terminal to the LEO satellite. Now, again, for display purposes, I've sped up this video. I think this is about 10 times speed. But this really allows us to see some of the effects of the channel characteristics as we're handing over between satellites. So we have the signal plot on the right-hand top again, and we see this Doppler profile or Doppler shift as the LEO satellite's passing overhead. We're also seeing that jump around. As a new link is established to a new satellite, the RLS 2100 will instantaneously apply the new channel characteristics for that link. We can see also the delay profile in the bottom plot changing in sync with this scenario that's unfolding. So this type of test could be very nice for a larger network test, perhaps, where the RLS 2100 can be a core physical layer piece of a network test, and you're maybe testing your satellite orchestrator with handovers between satellites. Or it can be simply back to terminal type testing where a user is very interested in their modem performance in the face of these changing channel conditions. So I'll stop that one. Go back to the slides for an introduction of the final demo here. Demo 3. And now we're really adding another layer of complexity by putting the terminal in motion. So that terminal on an airplane parked on a tarmac in JFK in New York is now going to fly a route from New York to London. And in addition to this added motion of the satellite, so bringing in a little bit of Doppler for the aero terminal, along with dominated by the LEO satellite, we're going to introduce some additional channel impairments, including phase noise, HPA nonlinearities, some reflected paths, and some interferes. So let me share my screen for this, for the third and final demo. Okay, we've also actually introduced here a ground station. So we have this bent pipe scenario now, where we have the RLS 2100 emulating the link from the ground station up through a LEO and down to a terminal ground station in Newfoundland, Canada here. And so along with all of the delay, Doppler, and path loss, we're now going to show some of the additional channel characteristics that can be applied with the RLS 2100. So here we're going to look to add some over-the-air impairments. So I spoke about fading, so multipath fading. So here we're going to enable this block. We have 2 reflected paths. So once we enable this, actually on the bottom right-hand side, we've replaced the delay profile plot with just a power profile plot, so power over time. And with these reflected paths being introduced to the signal path, we see this varying gain. We've also now just added some interference to the path. So a shape noise interfere on the left and a CW interfere on the right. The shape noise emulating some adjacent channel interference and maybe a jammer for the CW interfere. And now on top of this, we're going to add some channel characteristics of the transmitter. So adding phase noise here, we bring up the noise skirt. Really, that's some phase out far out phase noise we're seeing following this density plot. And similarly now for the HPA, we're going to apply this nonlinear characteristic. So for AM in this compressed region. And when that's enabled, we kind of see some of this spectral regrowth. So at this stage, we have all of these channel impairments in addition to the scenario that's unfolding. So you can see this not so insignificant effects here on your signal passing through. As we peel back these impairments, removing the HPA, the phase noise, onto the fading, removing the reflected paths, and the interference, then we get back to kind of our simple scenario, well, relatively simple, of just delay, changing path loss, and Doppler, along with satellite handovers. So in the power profile plot, we can see where the satellite handover occurred. So this is really the third demo that I wanted to show here, really highlighting the various channel conditions that we can account for in satellite link testing. So I'm going to stop sharing my screen again. Going back to the slides, I think the last 2 slides here. And so, okay, just a slide here summarizing the demos that we just went over. So yeah, demo 1 illustrated how even in with a stationary user terminal, the dynamic nature of LEO links, how that can present some unique testing challenges. Demo 2 highlighted both the challenge and importance of testing for seamless handovers with a satellite constellation. And Demo 3 really ramped up the complexity, showing the RLS 2100's ability to apply multiple channel characteristics in real time and showing the effect of these on your signal. So this brings us to our last slide here. So even as we look at the increasingly complex world of satellite communications, we stand on the brink of a bright future. This future brings with it a need for rigorous testing to ensure the reliability of satellite networks. The right testing approaches are crucial in this new phase of space tech. At Square Peg, we're proud to be at the forefront of this, partnering with ESA and numerous other organizations to tackle these challenges head on. And we look forward to what's next. If you're facing testing challenges or have questions about this complex landscape, we're here to offer our expertise and support. And so now again, on behalf of Square Peg Communications, I'd like to thank you for joining us today.
Thank you so much, Colin, and thank you so much, Square Peg, for putting on this webcast today. We're right up against time, so unfortunately, we don't have time to answer questions live. But for those of you who have answered questions here, Colin will reach out to you offline to answer those questions. And also, before you leave, if you go to the handouts tab on the right-hand side next to Q&A, there are some handouts and PDFs that you can download and take with you. So please feel free to take those with you before you leave. But thank you all so much for joining us. Thank you, Colin. Great presentation. And we will see everybody soon for our next Technology Webcast Series episode.
Thanks, Jeff.
Thanks, everybody.
Thanks, everyone.